I am Rohan, and I will be giving a talk on primarily applications of ordinals to some problems. And this is in one of our talks this year about higher math, so it's not really about contest math, although there is one slightly relevant concept from there that we will encounter. So the topic will be ordinals and two theorems, one of which is Goodstein's theorem. And I'm going to start by quickly reviewing what natural numbers are, because this is very important for defining ordinals. So natural numbers either start with 0 or 1. I'm going to start with 0. And then you have a successor function. From each one, you can get a new one by adding 1. So you can get to 1, then to 2, then you can continue. And there is no largest natural number, because if there is n, there is always n plus 1, which is larger. And motivated by this, we can think about how to define a sort of infinity. Infinity has to be greater than all of the natural numbers by definition. So one way we can do this is to define omega, which is going to be our smallest infinity, as the smallest number that is greater than every natural number. So one important thing to note here is that we don't have any such thing as omega minus 1, because we have this definition based on being greater than everything else. And if we define things in this way, we can't make smaller numbers. But we do have omega plus 1, which we can define as the smallest number greater than every natural number, and also greater than omega. In this way, we can also define omega plus 2, omega plus 3, etc. Each one, like for example, omega plus 4 is the smallest number greater than all natural numbers, omega, omega plus 1, omega plus 2, and omega plus 3. And one thing to note is that we can also extend this past just addition. If we take the smallest number greater than omega plus 1, omega plus 2, omega plus 3, and then omega plus any natural number, we get something that is omega times 2, because you can't represent that by omega plus n for natural n, because it would not be greater than omega plus n plus 1. And we can also define omega times 3 as, here it's slightly more complicated. It's bigger than omega plus 2, omega times 2 plus 1. But essentially it's the same definition, just with the coefficient of omega changed. And we can define omega plus 4. We can continue defining this. And eventually we're going to reach omega times omega, which is omega squared. And based on definitions like these, we can define basically any combination of natural numbers and omega using exponentiation, multiplication, and addition. So for example, omega to the omega would be greater than omega to the 1, omega squared, all the way until omega, well, not all the way until anything, just omega to any natural number. And one property about these ordinal numbers that seems counterintuitive is that any sequence or group of these ordinals, if you keep decreasing, you're going to eventually have to stop. And one way this seems very counterintuitive is because you can, for example, start at omega and then pick any natural number. And the natural number can be as big as you want, so it can take indefinitely long to terminate. But if we go from omega to a natural number n, for example, even though we cannot give any guarantees on how long it will take to terminate, because n can be as big as we want, the next number is at most n minus 1, then at most n minus 2. And from this, we get that there are at most n plus some constant amount of times this can happen. And the proof that any sequence of ordinals that's decreasing eventually has to stop and it can't be infinitely long is technical, so I'm going to not go into it in this talk. But it is an important result for the two theorems that we will be looking at today. So the first theorem is Goodstein's theorem. And one definition that's very relevant to this is base n notation. Here n is integer greater than 1. And what this is essentially for some number k, we can represent it as something times 1 plus something times n plus something times n squared. And we typically use base 10 notation, which means that, for example, the number 1123 is 1 times 10 cubed plus 1 times 10 squared plus 2 times 10 plus 3. And here, the coefficients of each of these, which I noted as a question mark, are all strictly less than n, and they are integers. Well, they're also at least 0. And from this, we can extend this to something called, I think it's spelled like this, hereditary base n notation. And for this, I will be using the example of 31 in base 2. So we can write, 33. Actually, no, let's just stick with 31. So we can write 31 as 16 plus 8 plus 4 plus 2 plus 1, which is 2 to the 4th plus 2 cubed plus 2 squared plus 2 to the 1 plus 2 to the 0. And this is how you express it in base 2 notation. But if we look at these exponents, they themselves are not in base 2 notation. So hereditary base n notation essentially takes this one step further and converts all the exponents to base 2 notation as well. So now we have 2 to the 2 to the 2 plus 2 to the 2 plus 1 plus 2 to the 2 plus 2 to the 1, and then we can just leave the last part as plus 1 because that is less than 2. If we had something such as 2 to the 5 in there, and sorry, 2 to the 8 in there, which we would write as 2 to the 2 to the 3, this 3 is still not in base 2 notation, so we would rewrite it again as 2 to the 2 to the 2 plus 1. And here we get something that's fully expressing the number in terms of 2 and the number is lower than it. So Now we can get to the statement of Goodstein's theorem. Let's say we have any number n. I'm going to stick with the example of 31 for now. And then we write its hereditary base 2 notation. We have 2 to the 2 to the 2 plus 2 to the 2 plus 1 plus 2 to the 2 plus 2 to the 1 plus 1. And you can call this stage 1. To go to stage 2, we take all the 2's here and we replace 2 with 3. So we get 3 to the 3 to the 3 plus 3 to the 3 plus 1 plus 3 to the 3 plus 3 to the 1 plus 1. And then we subtract 1 from whatever this is. Here there is already a plus 1 floating around, so we just subtract it. If we didn't have that plus 1, like if we were working with 30, for example, and we were trying to subtract 1 from this, we would have to remove it from hereditary base notation for some time. And we can, for example, compute this as a number, subtract 1 from that number in the normal base 10 system, and then convert it back. Or we can observe that when we subtract 1 from the underlined portion, it is 3 to the 3 to the 3 plus 3 to the 3 plus 1 plus 3 to the 3 and then plus 2. And when we do this with larger numbers, like if the 3 were a 4 instead, this 2 would be a 3, which would not be permitted in our original hereditary base 2 notation, but we're not using that anymore, so that's not a problem. Now, Goodstein's theorem says that if we continue this, taking our sequence from the second stage, replacing the 3's with 4's, and then we continue with that indefinitely, we are eventually going to reach 0, which seems really weird because we're increasing the number by so much, even when we're replacing the 2's with a 3, and replacing 3 with 4 should give an even bigger increase. Well, at each step, we're only subtracting 1, which is much less. Ultimately, it's because when you subtract 1, this is similarly motivated as how there's no such thing as omega minus 1 in the ordinal numbers. You can never have a minus 1. So if we look at the constant term, it's going to have to keep decreasing. And eventually, it's going to hit 0, after which the next term will need to start being broken apart into constant terms. Even with this intuition, it still seems really weird because this is just a small change and the rest of the terms increase so much faster. And in fact, if you only use the arithmetic of natural numbers, which is the standard math, then you cannot prove this theorem. So this theorem is independent of the natural numbers arithmetic. Because you can neither prove it nor disprove it only using those properties. But using ordinal numbers, you can prove this theorem. One way, and the only way that has been done as far as I know, is to create a corresponding sequence that sort of parallels this. So we have our example of 31, where we have, okay, I see a question. In the third stage, will this 2 remain a 2? Because it's not a 3. And this is fine because essentially in the base n notation, we want to keep reducing these 4 and 3 because they're bigger than the 2, and in base n notation, we want our coefficients to all be less than n. For example, this is essentially the same as all the digits being 1, 0, 1, 2, 3, 4, 5, 6, 7, 9 in base 10, and you don't see 10 as a digit there. But here you have a 2, which is less than a 3, so it can stay in that form for the same reason as why the 1 can stay in this form. And when you go to the next stage, you're replacing only the 3's here with 4's. So you get to 4 to the 4 to the 4 plus 4 to the 4 plus 1 plus 4 to the 4 plus 2. And then you have to subtract 1 from this, which will turn the 2 into a 1. So when you go from stage 2, for example, to stage 3, you're only replacing the 3's with 4's. Is that clear? Or, okay. So the standard proof for this is to create a paralleling sequence to the Goodstein sequence. And I'm going to demonstrate it for our example of 31. We start with 2 to the 2 to the 2 plus 2 to the 2 plus 1 plus 2 to the 2 plus 2 to the 1 plus 1. After the first stage, it becomes 3 to the 3 to the 3 plus 3 to the 3 plus 1 plus 3 to the 3 plus 3 to the 1, and then there's no plus 1 term anymore. And then it becomes 4 to the 4 to the 4 plus 4 to the 4 plus 1 plus 4 to the 4 plus 4 to the 1. And then when we have to subtract 1 from this, it becomes plus 3. And if we go back to our intuition, which tried to justify why this theorem can make sense, it was saying that the decrease in the sort of exponents of these terms caused by the constant -1 operation is significant, even though this replacing 2 with 3, 3 with 4, etc. causes a much larger increase. So this sort of motivates thinking about what happens if we, instead of using 2, 3, and 4 here, we just have a constant number. So with this, we can construct from each term a paralleling term by replacing, for the stage 1 term, we replace all 2's with omega. And then we replace all 3's with omega. And then we replace all 4's with omega. And here, it seems a bit more clear that the elements on the right side are decreasing, because we can break down the shift between stages into 2 parts. So in the first one, we replace the base number, which is essentially replacing 2 with 3, 3 with 4, and etc. And in the second stage, in the second part, we subtract 1. And if we look at our paralleling sequence here, the step 1 in this stage change does not actually change anything anymore, because when we go from, let's say we are starting with some expansion, and then we have the paralleling term which replaces 2 with omega. If we look at the result after step 1, it replaces 2 with 3. And in the paralleling term, we then replace 3 with omega. So they reach the same conclusion. And therefore, the first step, rather than causing some huge increase, now just keeps the sequence the same. But subtracting 1 will always make the term decrease. So we have that this is a decreasing sequence. And one common conception about how the proof concludes is that every term on the right side is greater than the left side. And if we can show that the right side goes to 0, we are done. A more proper interpretation is that this construction always exists given either one of these. For example, if we have something like omega to the omega to the omega plus omega to the omega plus 1, etc. When we're on stage 3, we can get back here by replacing each instance of omega with a 4. And we can also go back with our construction of the parallel sequence. So that means that the one term from the original sequence exists exactly when the term in the paralleling sequence exists. So we want to show that the paralleling sequence is finite. It cannot go on infinitely long. And as we showed just now, the terms are strictly decreasing. And I mentioned before that any decreasing sequence of ordinals eventually reaches 0 or stops. So, and I'm not going to prove that because I think it would be too technical for this talk. So the paralleling sequence cannot go on infinitely long, and therefore the original sequence cannot go on infinitely long either. So therefore, we have finished this proof. And the statement that this theorem is independent of natural numbers is much more complicated and technical, and it requires a much harder proof as well. So that is not going to be within this talk, but this is one application of how you can take a seemingly counterintuitive problem that would be really hard to think about concretely. And then using ordinals, you can make it doable much more easily. So now there is a second example, and this is a problem from Kirby and Paris, who are the same people that proves the statement about Goodstein's theorem being independent of natural number arithmetic. So here we have a game. So I think it's phrased in the paper as Hercules is fighting a Hydra, and every time Hercules cuts off an edge, which has to be one of the outer edges of the Hydra, and the outer edges would be the ones connected to these nodes. So every time Hercules cuts off one of these edges, you go back downwards one step, and then you create, if you're on stage 0, for example, you look at what you have remaining along this path, which would just be this, and you create one copy of it. So that copy would be here, and it is now connected to the same node. And then on stage 1, you can repeat the same thing. You take off this edge, you go back here, and now this is the part being duplicated. So you have 2 copies of this added now because we are on stage 1, and those are added here in the next stage. And this continues. And here the problem is to show that Hercules will eventually fully kill the Hydra, which again seems very counterintuitive, especially because there is another condition in the problem, which is that Hercules does not find a best strategy and enact it. He just plays randomly, but even then he is guaranteed to win. Okay, I have a question. Did we explain how they duplicate? So let's say we're on stage 0, and we take one of the outer edges. So outer essentially means that you have a vertex that only is connected to one other. Then you take the edge connected to it and you delete it. Now you can go back to this vertex and look at what you have remaining from there. In the example I just drew in, there's nothing left, so nothing will be duplicated. And the original example in the diagram, we're deleting this edge. So now we have this as our resulting Hydra. And we deleted at this vertex, so we go down by 1 edge and we reach this vertex. Now we look along this line and see what portion of the graph is here, and it is this part, because essentially if you cut off this vertex from the graph, that is the part that would be separated. And if you're on stage 0, you add 1 copy of the portion that I put in dotted lines to the blue vertex. So one of these is from the original thing because we didn't delete it, and another one is added. In future stages, we do essentially the same thing, but if we were in stage 3, for example, rather than adding only 1 copy, we would add 4, and this continues indefinitely. Okay. So, I don't remember exactly where I was, but essentially the problem is that no matter how Hercules plays, you want to show that he's guaranteed to fully kill the Hydra. And this makes use of some topic that you may have seen from more advanced contest math. It's pretty useful there. It's also somewhat useful in higher combinatorics. And there's an invariant. It's essentially a property you assign to something that never changes. And it has an accompanying thing, which is a monovariant. And a monovariant is similar to an invariant. It's a property you assign to something, except it either always decreases or always increases. And the standard example for this is if you have like a list of numbers on a board and you replace two numbers with their sum, then the sum of the numbers written on the board will always be a plus b plus c plus d plus e. So if you want to figure out what the last number written would be, it must be that. Here, we can assign an invariance to the Hydra based on ordinals. So I'm going to erase the drawing on the stage 0 diagram to explain how this works. The previously mentioned outer vertices, which are only connected to one other, can be assigned 1. Then for each vertex on the next level, so it's 1 down from one of these vertices, we take the sum of omega to the number above it. So here it would be, actually no, I think you assign 0 to these. And then the vertex below it, you assign the sum of omega to the 0 plus omega to the 0 plus omega to the 0, which is here 3. Here you only have one vertex above it, so it would just be 1. Same thing here. And this one is a bit more complicated because aside from being immediately below this vertex, it's also immediately below this one. So we don't assign anything to it yet, but we do assign omega to the, and sorry, we assign omega to the 0 plus omega to the 0, which is 2 for the vertex connected to these two. Then we can continue going a level further. This one is only connected here, so it would be omega. And now this one is connected to a 3 and an omega, so it would be omega to the omega plus omega to the 3. Well, this one would be omega to the omega squared plus omega to the 0, which is 1. And finally, at the bottom, we have omega to the omega to the omega plus omega to the 3 plus omega to the omega squared plus 1. And this is fundamentally the same idea of assigning a parallel sequence to the Goodstein sequence, except here we are assigning a parallel ordinal number to the Hydra. And what we want to show is that if we keep track of this number between stages, it will eventually reach 0, which is the state when, and when I say the number, I'm referring to the one on the bottommost point. And we want to show it eventually reaches 0, which is the state when it's the only point there. We can also go through the stage 1 diagram as an example. And if we want to know precisely what order we go in when defining this, we can think about it in terms of how far away it is from the bottom. So this one is the farthest away from the bottom that isn't already a 0, so it becomes a 1. Then we have omega to the 0 plus omega to the 0, which is 2. We also have 2 here, well, we have omega there, and 2 there. Then here we can compute omega to the omega plus 2 omega plus omega squared times 2, because there are two 2's. And then this one is omega squared plus omega to the 0, which is 1. And then the final one would be omega to the omega to the omega plus omega squared times 2 plus omega squared, omega to the omega squared plus 1. And if we look at these terms side by side, okay, we have omega to the omega plus omega to the third plus omega to the omega squared plus 1. It's in stage 0, and in stage 1 we have omega to the omega plus omega squared plus omega squared plus omega to the omega squared plus 1. These terms are the same, but stage 0 is bigger because omega cubed is larger than omega squared plus omega squared. And we can remember this because omega cubed was defined as a number bigger than omega squared times 2, omega squared times 3, etc. So it must be bigger than omega squared times 2. And fundamentally, a way we can motivate this is similar as in the Goodstein sequences. This result seems very counterintuitive, but there is one way you can try to make sense of it, which is that sort of the depth of the graph doesn't increase. And through this definition of the ordinal we associate to the hydra, we can keep track of, in a way, the distances from the head of the hydra, which is the lowest point, to all the farthest parts of it. And the reason we use omega here is to make sure that even when there are more parts added to the same place, that doesn't cause as much of an impact as how far away they are. And because of this, when we, for example, take away this 0, this edge here, even though we're adding something else, its distance from the head is lower, so the degree in omega of that part, which we can see here, is lower than the corresponding degree. And because of this, the ordinal we associate to the hydra is going to always decrease. And again, because ordinals can only decrease finitely often, it is guaranteed to stop eventually and reach only the head of the hydra, after which Hercules will have won without any strategy. And as before, this result is also independent of the natural number arithmetic. So I'm not going to cover that either because it's also really technical and it's beyond the scope of this lecture. But in recap, we looked at the definition of natural numbers as essentially starting with a 0 and then repeatedly adding 1. And this adding 1 thing is effectively the same as, for example, 2 is the number that's the smallest number that's bigger than 0 and 1. 3 is the smallest number bigger than 0, 1, 2, etc. And we extended that to infinities. So we took the smallest number bigger than every natural number, and then bigger than things even including that omega. And then when we had an example of Goodstein's theorem, where the number was increasing too much to be realistically measured, we just replaced it with omega so that that change would be halted and we can focus instead on the eventually more impactful -1 operation. And we did a related thing in this example where we noticed that in a way the distance from each of the farthest parts of the hydra from its head do not really increase, although there are many more heads. And therefore, through this measurement, we can see that every time we cut a head off, while the coefficients may increase, the degree itself will not, and therefore this will also always decrease. Therefore, it will have to reach 0, and the Hydra is guaranteed to be killed. And like in Goodstein's theorem, we have no guarantee on how long this can take, because again, one way to think about this is that if we want to make the process take, because our bound comes from using the fact that an ordinal sequence that's decreasing has to eventually reach 0. But if we want this process to take, for example, 50 steps, we could take the ordinal sequence omega to 50 to 49, etc. And there's no guarantee we can construct a hydra from that, but that conceptually explains why we can't provide a guarantee on how long this would take in general. In specific examples, like when you have a specific hydra, it can be computed. And it can also be computed for a Goodstein sequence, but these numbers are extremely large and are generally not very fun to work with. And this talk relied mostly on the work by Kirby and Paris about these two results that are independent from piano arithmetic, which is just the natural numbers, and by Goodstein's original work on his theorem. That is all for the talk. Thank you for attending.
Any questions? So if you have any question, feel free to unmute yourself and ask a question. Otherwise, I'm going to stop recording here. And